If you use a smart telescope like the Vaonis Vespera, you already know how it operates and simplifies capturing the night sky. But dealing with light pollution remains a persistent challenge, particularly when you want to photograph faint emission nebulae. Today we are taking a closer look at the Vaonis Dual Band Filter. We will examine the technical reasons behind what it actually does, discuss when it is genuinely necessary, and look at the physical integration. Hi, I'm Bogdan Damian and welcome to another video review. To understand how a dual band filter operates, it helps to look at the light spectrum. The night sky contains broad spectrum light from different sources like street lamps, residential lighting, but also the moon and starlight in general. This broadband light often obscures the faint signals from deep space objects. A dual band filter is designed to completely block out almost the entire visible light spectrum, only permitting transmission at two specific narrow wavelengths, hydrogen alpha and oxygen 3. Let's break those down. The first band is hydrogen alpha or H alpha. In terms of wavelength, this sits right around 656 nanometers, which falls deep in the red part of the visual spectrum. Hydrogen is the most abundant element in the universe. When clouds of hydrogen gas are energized by hot young stars inside them, they become ionized and emit light at this exact 656 nanometer frequency. This is what gives targets like the Rosetta Nebula or the Horsehead Nebula their rich, intense crimson color. The second band is oxygen 3 or O3. This wavelength sits right at 500 nanometers, which looks teal or blue-green to our eyes. This light is emitted by doubly ionized oxygen. You'll find incredibly strong O3 signals in planetary nebulae like the Dumbbell Nebula and the outer shells of supernova remnants like the Veil Nebula. What makes a dual band filter so powerful is its band pass, the width of the window it leaves open. Good dual band filters only let in a sliver of light around these two exact lines, usually just a few nanometers wide. Because common light pollution sources like high pressure sodium or mercury vapor streetlights emit light at completely different wavelengths, they bounce right off the filter. By isolating the 656 nanometers red and the 500 nanometers teal light, the filter increases the contrast between the emission nebulae and the background sky. Now, if you are using a Vespera telescope, you already have a bit of an advantage. Out of the box, it features a built-in UV IR cut filter. This is great for broadband targets. If you are shooting star clusters or galaxies like Andromeda, the built-in filter is exactly what you want. However, emission nebulae require a different approach. When imaging targets heavily obstructed by atmospheric skyglow, the standard UV IR cut filter is generally insufficient. Isolating the specific details of glowing gas under light-polluted conditions requires a much narrower bandpass, which is where the dual band filter becomes relevant. One crucial detail regarding the Vespera ecosystem is the mounting system. The telescope does not use standard threaded filter rings, meaning that you can't just take a regular 2-inch filter and screw it into the front. Vaonis uses a proprietary filter mounting system which allows for larger filters to be mounted. So if you want a filter, you are heavily encouraged to buy their specific filter, and at $399 it's a well expensive filter. So let's see if it's worth it. Physically, The filter weighs 17 grams and measures 78 millimeters in diameter by 6 millimeters thick. The frame is constructed from black plastic that houses the optical glass. The glass surface is significantly larger than on a 2-inch sized filter, with the diameter measuring 51 mm compared to the 44 mm of a standard 2-inch filter. The primary difference in its construction, aside from the glass surface, compared to a standard 2-inch filter, is an electronic microchip embedded directly in the rim. When you attach the filter to the telescope's optical arm, this chip communicates with the telescope's onboard computer, allowing the telescope to automatically detect the filter's presence. As a result, it recalibrates the autofocus to account for the added glass and adjusts the observation parameters inside the Singularity app. It is a fully automated process, meaning you don't have to manually change your exposure settings in the app before you start observing. Optically, the Vaonis Dual Band Filter is made out of high-quality optical glass and is fully multi-coated. It also isolates the hydrogen alpha and oxygen 3 emission lines with a narrow 12 nanometers bandwidth. This should make it particularly effective for observing emission nebulae, whether in light-polluted urban environments or under dark skies, as it reduces starlight and makes the nebulae stand out, especially in dense star fields. But the real question is, how well does it really work? Let's look at the results. I had the filter for a few weeks now, and during which I had the chance to test it on multiple nights from my backyard under Porter 4 skies. My first target was the NGC 7000, aka the North America Nebula. Here's the target shot without a dual band filter. You can clearly see how overwhelming the stars look, and the background is really bright. The nebula itself lacks definition. And here is the exact same target with the Vaonis Dual Band Filter attached. The difference is significant. The background sky is completely black, the stars are tighter, and the glowing gas suddenly pops out. Here is another example, M42 or the Orion Nebula. You can clearly see what a big difference the filter makes. There are suddenly a lot more beautiful details visible once the broadband noise is eliminated. And then there is the problem with vignetting. This always is visible as the telescope tries to compensate for the lack of light, increasing the brightness around the edges of the frame. Here I need to mention that a standard 2-inch dual band filter mounted on a regular telescope will perform similarly, provided the filter is of a decent quality. At this point, you might be asking yourself why not simply 3D print an adapter to fit regular 2-inch filters instead. This seems like the sensible thing to do, especially if you have a 3D printer and already have a quality dual band filter. The short answer is yes, you can, but it's not worth it. I printed an adapter and the filter fits perfectly. You can even buy a specific electrical resistor and add it to the printed ring so that the telescope correctly identifies it as a dual band filter. At first glance, it also seems to work like a charm, with the Vespera identifying the filter without hesitation. And from afar, the images also look really nice, showing significantly more details on deep sky objects compared to images captured without a filter. It seems like the ultimate budget hack, but there is a massive problem. Let's take a closer look at the North America Nebula. Zoomed out, this actually looks pretty good. But once we start zooming in, we notice that all the stars look like little triangles. At first, I thought it was a printing error, I went back, reprinted the adapter using different infill configurations and adjusted the tolerances, but the result was always the same, triangular stars. Here is M42, same story. Overall nice, but when zoomed in, the stars appear all funky and weird. I've tested the 2-inch SV220 from SV Vaonis on a regular telescope, and the stars were perfectly round, so the glass itself is fine. So what's wrong? Well, it comes down to microalignment, tolerances, and the physical size of the filter glass. The Vespera's optics, like those of any optical instrument, are very sensitive. Even the slightest tilt of the 3D printed adapter or uneven pressure pinching the glass as it screws into the plastic introduces severe astigmatism into the optical path. The size difference 51 versus 44 mm also contributes to a less than perfect result. So while the DIY route is fun and cheap, if you want crisp, perfectly round stars and the absolute best image quality, you really have to bite the bullet and use the official Vaonis filter. Anyway, that's been it. I hope you all enjoyed it. Let me know what to think about the Vespera dual band filter and about dual band filters in general. Do you actively use filters to improve your astrophotography? I'm very much looking forward to reading your opinions in the comments below. Thanks for watching and catch you guys in the next one.